Okay, so one of the more interesting and bigger problems that we face in the groundwater world is something called aquifer compressibility. And what happens to your aquifer is that, remember, it's rock, right? And it's got pore space. And that pore space is just an opening. And if put under enough pressure, a rock will squish enough to compress those openings. But when there's water in the pores, because water is not compressible, all of that weight, that lithostatic pressure we've talked about in the past, can't squish the pore as long as there's water in it. It's kind of like having rock in it. Rock isn't very compressible and water isn't compressible. But if you take the water out, then suddenly those pores can start to collapse. And this image that I have up here shows where the ground surface was in various years. So this is the San Joaquin Valley of California, big agricultural area. They really started irrigating it with groundwater to a large degree sometime around World War I. So up on the top of the pole, that's where the ground surface was in 1925. And then you see another one in 1955, and where he's standing now, that photo was taken in 1977. So they had actually sucked enough water out of the ground to spread over fields, irrigate fields, so that the pores in the aquifers below the land surface started to collapse. When they collapse, it basically reduces the volume of rock, and the whole surface just comes down, 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 down. And you can see this area, that looks, if that guy's 6 feet tall, it's pushing 30 feet. So the ground surface has dropped 30 feet in 50 years. That's half a foot a year. I mean, for your ground to be sinking 6 inches a year because people are sucking water out of it at such a rate that all the pores are collapsing, that's rather stunning. And also leads to an awful lot of problems because we have things like buried gas lines, buried power lines, and these areas don't sink evenly sometimes, so you get this differential settling, houses end up crooked, power lines get snapped, all these utilities end up pretty messed up. So this is a big topic in groundwater. And it's actually pretty easy to figure out how much of this is going to occur with some really simple measurements. So let's kind of take a look at this topic with what time we have remaining in class. So this is compressibility of aquifers. And the other bad thing about this that you have to remember is once you squish those aquifers, or once you squish those pores, you can't unsquish them. You can't somehow inflate your aquifer back to where it was. You reduce the porosity, you reduce the permeability, and you reduce its ability to be an aquifer. It's not going to transmit water the same in the future. So let's take a little chunk of rock. Okay, that rock has some pores in it. And those pores are filled with water. Okay? Now this rock is under the ground. So it's being squished by lithostatic pressure. Do you guys remember how to calculate lithostatic pressure? We've done it quite a few times. I don't know if you'll remember off the top of your head, but you might be able to think through it. Keaton wants to try.
Density times height times gravity.
Perfect. So density, what units do we use for density? Kilograms per meters cubed. Height, or we're going to call, let's see, depth. Let's use D for depth. Measure that in meters. And then gravity, which here is 9.8 meters per second squared. So density times depth times gravity. Now, just a couple notes that we already talked about. Water is nearly incompressible. Ever so slightly compressible. But because it is so hard to squish, it provides a lot of support, so it won't compress or collapse with the static pressure. So think about this here for a minute, okay? We have some lithostatic pressure pressing down, okay? We can think of that as pressure. Engineers like to think about it in terms of stress. So the total stress that's pushing down on this rock, you can think of it as being the weight of the overburden. If you don't like that symbol, you can just use P for pressure. So it's the weight of the overburden pressing down on the aquifer. It's trying to collapse that aquifer. But if this is in equilibrium, then that aquifer is fighting back, right? So in those pores, we have some water that's under pressure. So this is the pressure exerted by water. Plus, you have the rock there, right? And the rock's fighting back too. The rock is not compressible. So we use this little delta R. So this is what we call the effective stress. You can think of it as rock strength. That's providing support. So you got lithostatic pressure that's trying to squish this thing, this system, this rock with water in it. The rock is pushing back on it because all these rock grains are touching. And the water's fighting back too. The water's sort of acting like a little rock fragment as well. What happens, though, if... So say it's in equilibrium now, okay? Everything's good. Got this aquifer. There's a bunch of rock above it. Gravity's pulling it down, squishing the rock, but the rock's fighting back, and the pores are fighting back because they have water in it, okay? And so it can't get squished. But what happens if you start sucking water out and the water pressure goes down? Then suddenly this value here, this total, is going to be larger than this, isn't it? If you reduce that second term, then suddenly it might not have enough pressure to fight back against the overlying stress from the overburden. So another way to think about this is that if your water pressure drops because humans are extracting water from the pores, then the rock may not be able to withstand that pressure, lithostatic pressure. And the pores may begin to collapse. And really what's going on is that the aquifer collapses. Remember, these are mostly sedimentary rocks made of little grains of sediment, sometimes cemented together, sometimes just sort of packed together tightly. So the aquifer collapses as grains in the sedimentary rock shift. In response to the additional stress it now has to fight back. Because the water is no longer providing it. And also, different types of rock may collapse differently. Some may collapse more easily than others. So to sort of put this all together, hydrologists have come up with a little relationship. This is aquifer compressibility. This is a property that varies from aquifer to aquifer, depending on what rock it's made out of. For example, shales compact differently than sandstones. And even some sandstones will compact differently than other types of sandstones, depending on how they're put together. Yeah?
What Greek letter is that?
That looks like, is that alpha? I don't know. I'm not good with Greek letters. I'll have to look it up. So again, shales compact differently than sandstone. and limestones. And all of them act differently than igneous or metamorphic rocks. Some rocks are just stronger than others and resist compaction better than others. And as I said before, you can even get compressibility differences between different kinds of sandstones. For example, depending on how they're packed or how they're cemented. So different rocks resist compaction differently. But if the stress is high enough, they're going to compact. So here is kind of the definition for aquifer compaction. So again, this little, I think it's alpha, is our value for compressibility. Its units, which I'm not going to spend much time on because we're going to do some calculations here in a minute, are meters squared per Newton. Newton is a measure of stress or pressure. B is the original aquifer thickness. And again, like most of these equations, none of this will make sense till I give you a example, which is coming. dB is the change in thickness. How much it compacts. And dP is the change in water pressure in your aquifer. And the change in water pressure is pretty easy to calculate. It's going to be dH, which is the change in hydraulic head. Again, this will make sense when we do an example, times density of water, typically around 1,000 kilograms per cubic meter, times gravity, 9.8 meters per second squared. All right, now that you have all this down, probably doesn't make a whole lot of sense, but I have an example that I think, and it's pretty easy. Actually, this one of the easier things I have you do this semester. Let me give you an example. I'll let you finish your notes here. See some of you still writing. Okay. Guys ready? All right, let's have an example here. I'm going to write it out and I'm going to draw a little diagram to go with it. Hopefully help illustrate the point. So let's say our buddy Blake has a well. That taps into confined aquifer. So hopefully you're getting a little image in your head of what a confined aquifer is looking like. Confining layer. Blake's not too bright, so through wasteful water use, the total head of his well has dropped 53 meters. That's a lot. This could be not Blake, it could be a golf course. It could be rancher Barb who is irrigating the bejeebers out of everything, you know. But whatever reason, they've sucked enough water out of the well that total head is dropped by 53 meters. The aquifer was originally 45 meters thick. So get that in your head too. Basically, it's a rock unit that's about half a football field in thickness. The aquifer is sandstone, has lots of pore space. All these little sand grains are touching. Now you can look some of these up online in hydrology books. People have looked at the compressibility values for different rock types, and a common compressibility value for sandstone is 1.8 times 10 to the minus 8th meter squared per Newton. Pretty small value, right? And it should be a small value. Because rocks are hard to compress. Because rocks don't compress easily, their compressibility values are pretty small. And some rocks are less compressible than others. Igneous rocks are really hard to compress. They have values that are much smaller than we have for most sedimentary ones. Okay, so the question I'm going to ask you is how much should his aquifer compress? So before we sort of plug and gun here, let's sort of draw this out. We'll just make a real simple case. Here's our ground surface. Here's his well. I'm not going to draw this to scale, but let's go here. Here's our confining layer. And down here, here's his aquifer. It's sandstone. Now, originally, when he put in this well, the water rose to way up here. H1, okay? But Blake's been pumping this well for a while. So he's sucking water out of all these pores. And that's reducing the pressure in the pores because he's taking the water out. When you reduce the pressure in the pores, your pressure head value is going to drop. So your overall head value is going to drop. And after some time, he has managed to drop his well level by 53 meters. So H1, this is the original total head. And H2, total head after pumping for a while. So Blake's been sucking water out of this confined aquifer. Okay? There's less water in the pores. So the water in the pores can't fight back with the same amount of pressure that they used to. So now you have more stress on the rock, and that sandstone's going to feel it, and the grains are going to start to shift, and those pores are going to start to collapse. Okay? So that's mentally what you should see going on here. Okay? So now we can go back to our compressibility equation. Alpha equals change in your aquifer thickness over the original thickness over the change in pressure. All right, what do we know?
The change in thickness was negative 53 meters.
Okay, that was the change in head values is 53 meters. What else do you know? You know the compressibility, which was, I think we used 1.8 times 10 to the minus 8 meters squared per Newton. What else do we know?
The original aquifer thickness.
So we know B was 45 meters. We want to solve for what? Change in thickness. This is what we're after, okay? So you can arrange this, you can rearrange this equation a little bit. Several ways to go about it. I'm going to take the, hopefully the easiest way. Let me rewrite that. D. We have our compressibility value, 1.18 times 10 to the minus 8 newtons per meter squared. Our change in pressure, remember this value right here from our previous page of notes is the density times gravity times the change in head value which is 1,000 kilograms per meter cubed times 9.8 meters per second squared. And the change in head value was 53 meters. We can multiply all those together to get our value. I think it comes to 519,400 pascals. Pascal is the same as a Newton per meter squared. I actually wrote this, unit wrong here. Sorry, I wrote it upside down. 1.8. Making up numbers, making up values, doing all sorts of stuff wrong tonight. All right, that looks better to me. Probably looks better to you. Okay, so 1.8 times 10 to the minus 8 meters squared per Newton times our change in pressure, which is now over here, 519,400 newtons per meter squared, times B, 45 meters, well, we can cross out some units here. Meter squared, newtons. We're left with meters. And if you get the answer, let me know. And think about whether it makes sense. Could a 45-meter aquifer compress more than 45 meters? No, it can't. It's not likely to compress anywhere near that much. So it should be something less than 45 meters. Did you get a value?
I got 0.42.
And that's what you should get is 0.42. So half a meter. That's a lot. Especially if you have a buried gas line. So again, what this all means is, you sort of write this out in words. So according to this equation, compressibility equation, the aquifer compacts by nearly half a meter, 0.042 meters. And the reason that it collapses is that is a response to Blake extracting enough water to lower the pressure head by 53 meters. We use total head value, but remember, total head is elevation head plus pressure head. We didn't do anything to the elevation head, so all of the change in the total head was due to the pressure head. So you lowered the pressure head by 53 meters. That pressure was used to support the aquifer. Now it's not there. So that puts more stress on the rock. The rock starts to shift, starts to compress. And something you should realize about this is that even though the total head dropped by 53 meters, the aquifer is still saturated. All those pores still have water in them. How do we know that the aquifer was still saturated?
The level of the total head is above
The total head was above the confining layer, right? So that means that your aquifer still had to be saturated and still under some pressure. Blake can still suck more water out of that thing. Now eventually he'll get to the point where he will start to drain that aquifer, and then it's going to pack down even faster. So you can think of it this way, that all expelled water during pumping, I don't know why it's pink. Is from water stored under pressure in the aquifer. So when your water pressure drops, the water is fighting lithostatic less so than it was before. So it means that the rock has to pick up the load that the water no longer can, and it's going to start to shift around and collapse in response to the greater workload it has to do. Okay, so what I want to do is I'm going to leave you with a problem to work on over the next week. I'll go through this at the beginning of next class. This will just give you something to practice on. So let's say Dave has a well. That taps into a confined aquifer. The initial thickness of the aquifer is 45 meters. I think that's what we used in the previous example. In 5 years, his land has settled by 0.2 meters. And the total head in his well has dropped 25 meters. So my question is, what is the compressibility of his aquifer? And then a second part of this is Dave has a new neighbor who put a new well into the same aquifer that Dave has been using. Dave's neighbor, however, has heard about Dave's little issue with the ground settling. And obviously wants to avoid the same problem. And he would like to keep settling on his land to less than 5 centimeters. So the question is, how much head loss can Dave's neighbor allow to keep compaction to less than 5 centimeters? So try to go through this before next week's class. I probably won't put next week's class up until next Thursday. I get back late Tuesday night. I'll do this Wednesday and hopefully have it up Wednesday night or Thursday morning. So probably Thursday. So these two shouldn't take you too long, just a couple minutes. See if you can go through them and figure them out. And I will see you in person in a couple of weeks. Okay?